Okay, so this is a great demonstration of the fact that, like energy and linear momentum, angular momentum is a strictly conserved quantity. So let me remind you what angular momentum means. Okay, so angular momentum is a vector, and so if we have a rigid body, say rotating like this, then we curl our fingers in the direction of rotation, and then our thumb points in the direction of the angular momentum. Angular momentum is a vector. We could take that same object and we could rotate it in this direction. So we curl our fingers around the object, around the rotation, and then our thumb points in the direction of the angular momentum. Angular momentum is a vector. So if you have an angular momentum of an object in this direction, then it's rotating this way. And if you have an angular momentum of that same object in the opposite direction, it's rotating in the opposite direction. It's counter-rotating, okay? Very good. So now the idea that angular momentum is a conserved quantity means that if we have an isolated system, then if the angular momentum of one part of the system, say, increases along this axis, then it must be true that the angular momentum of some other part of the system must increase along the same axis by the same amount, but in the opposite direction, so that they are counter-rotating. Okay, so that the total change in the angular momentum is zero. It's exactly like a linear momentum. Okay, so I am a mass floating out in the middle of empty space, and there's a block here with some mass. I push on that mass, and that mass gains linear momentum along this axis in that direction. But then F12 equals minus F21, it's the same force acting over the same time, transferring exactly the same amount of linear momentum, but in the opposite direction, so that that vector plus that vector add to zero. And so there's no net change in the linear momentum. Okay, started with zero linear momentum, we push off, it stays with zero total linear momentum. Okay, linear momentum conservation. Okay, so now for our isolated system, it's going to consist of two parts. One is me rotating on this frictionless chair here like this about a vertical axis, and the Earth. This is number one, this is number two. Okay, and this system is isolated. So in order to dispel any potential confusion that can result from, oh, the Earth is spinning and this and that, we're going to consider a simplified situation, which gets at exactly the same physics. So I want you to imagine in your mind that the Earth is a great big ball of rock, which is floating out in the middle of empty space, and is at rest in an inertial reference frame and not rotating. And I'm sitting on top in this chair, okay? And this system of me and the Earth are isolated. There are no objects out here exerting external torques on the stuff inside this, inside this system, me and the Earth. And so the total angular momentum of me and the Earth can never change. If it starts out as zero, I have zero angular momentum now, and the Earth has zero angular momentum, it will always remain zero. Okay, now before we go on, I want to point out that whenever we talk about torque or angular momentum, it's always torque or angular momentum about a certain point, a fixed point in an inertial reference frame. The most convenient choice in this reference frame is right here, my center of mass location. So all torques and angular momentum will be evaluated about that center of mass point. Okay? Moreover, the kinds of torques and angular momentum that we need to consider are only in the vertical direction. So vertical up or vertical down. We don't need to consider any horizontal torques or horizontal angular momentum. Okay? So we will always consider torques and angular momentum about an axis passing through my center of mass. All right? And they can be up or down. Now, now to say that we have this isolated system of me and the Earth means that if my angular momentum increases in the upwards direction, then the Earth's angular momentum must decrease in the downwards direction. Okay, so right now I have zero angular momentum, the Earth has zero angular momentum, I do something and oh look, now my angular momentum has increased in the upwards direction. Conservation of angular momentum tells me that the Earth must have gained angular momentum in the downwards direction. So I am rotating this way, the Earth is rotating this way. Okay, now of course, angular momentum is moment of inertia times angular velocity. So I've got some angular momentum now. That's equal to my moment of inertia times my angular velocity. The Earth has exactly the same amount of angular momentum in the opposite direction. with the same magnitude. And that magnitude is equal to the moment of inertia for the Earth, which is huge compared to my moment of inertia, times the angular velocity of the Earth. Because the moment of inertia of the Earth is so large, it can store the same magnitude of angular momentum I have with an extremely slow angular velocity. So when I do this, then I get some angular velocity. But the Earth also gains angular velocity, but extremely tiny amount, in order to store the same amount of angular, the same quantity of angular momentum, magnitude-wise. Okay, it's just like me, this block out in space. If we have this block, if this block is supermassive, like the mass of the Earth, I push. For sure, I'm transferring a certain amount of linear momentum to that block, and exactly the same amount of linear momentum has been transferred to me, but in the opposite direction. Because my mass is relatively small, I have to be moving pretty fast to store that amount of linear momentum. This big, huge block, the mass of the Earth, it can store that same magnitude of linear momentum with a very small linear velocity. Okay, same thing for the Earth and rotational motion. Okay. Okay, so that's great. So if my angular momentum goes up, then the Earth's angular momentum goes up in the opposite direction. Okay, that's conservation of angular momentum. But what's more interesting is, well, how did that transfer of angular momentum work? Because I used to have zero angular momentum. All of a sudden, I ended up with some angular momentum. Some angular momentum in the upwards direction must have been transferred into me. From where? Well, from the Earth. So we have pulled out of the Earth angular momentum in the upwards direction. We have removed from the Earth angular momentum in the upwards direction, which means we have added to the Earth angular momentum in the downwards direction. So the Earth is now spinning this way, and I spin this way. Okay, so but how does that transfer happen? Well, let's talk about linear momentum. So when I have my block here, what transfers linear momentum is a force acting over time. So I push on that block, and so that force acting over time transfers linear momentum to that block in that direction. But then F12 equals minus F21, that block exerts a force exactly the same magnitude, opposite direction, back on me. And that force acting over the same amount of time transfers exactly the same amount of linear momentum to me, but in the opposite direction. So to transfer linear momentum is a force acting over time. To transfer angular momentum, it is a torque acting over time. Okay, so how did I get myself spinning like this? How did I transfer angular momentum to me? Well, there was a torque involved. And so how did that happen? Well, you'll notice that I touched the floor and can say, so what I did was, I used the fact that there's static friction between my boot and the floor, and so then I pushed like that on the Earth. Okay, so I exerted a force on the Earth at that point. Okay, and so that point is located some lever arm distance or a moment arm distance away from my axis of rotation, and so that force applied at that point is a torque, and the torque is r cross f. This is r, this is f. R cross f is a vector pointing down. So the torque, the twisting force that I'm applying to the Earth, is clockwise, down. Okay, and so that twisting force acting over the time that I'm pushing is transferring angular momentum in that direction into the Earth. Okay, and so from me, okay, and so I am removing downwards angular momentum from me, which means I'm adding upwards angular momentum to me, okay, or vice versa. Okay, so when I push on the Earth that way, then the Earth pushes back on me that way. So now it's being applied at a moment arm distance like this. So the torque, the corresponding torque is R, cross F is up. And so the Earth is exerting an upwards torque on me. And so that upwards torque acting over time, the time that I'm pushing on the floor, that torque is transferring angular momentum, upwards angular momentum into me. Okay, so from the Earth, we are removing upwards angular momentum, which is the same, which comes into me, which is the same as adding downwards angular momentum to the Earth. And so we end up counter rotating like this, okay? And I've got angular momentum like this, the Earth has angular momentum like that, and the sum is equal to 0. We started with 0 total angular momentum. Right now, we still have total 0 angular momentum, okay? So that's great. So it's very important that we understand how angular momentum is transferred between one part of a system and another part of a system. And just like F12 is equals minus F21, torque 12 equals minus torque 21. And so the transfer of angular momentum is exactly like that. Okay, so the total remains 0. Okay, so that's great. So we can transfer angular momentum between parts of this isolated system. And the way we did it is we used the fact that I could push on the floor. But what if I agree to not touch the floor? Okay, so I touch the floor to begin with, and then I apply a torque, and I transfer angular momentum into me and out of the earth. So there we go. Okay, but let's suppose that we agree now that I will not touch the floor. Well, then I am isolated from the earth, and there's no mechanism left for me to transfer angular momentum from me back into the earth. So whatever angular momentum is in me right now will stay there forever. Okay, so it's like this. If I wanted to push on a block, okay, and if that block has friction, great. There's like static friction, and so I can push on that block, and I can transfer momentum to that block. But if there's no friction, if it's a frictionless surface, I can't get that block to move. I can't transfer any momentum. Okay, it's exactly the same thing with this chair. So this chair is frictionless. Okay, so I can go like this and I can go like this, but I'm not exerting any twisting force on the earth because this is frictionless. Okay, it's like this, frictionless. I can take the chair off and I can go like this, and yeah, now I've exerted a clockwise torque on the earth. Okay, because there's friction there. But if there's no friction, then I cannot, no matter what I do sitting in this chair, I cannot exert a torque on the earth. And the earth cannot exert a torque back on me, so there can be no transfer of angular momentum between me and the earth. So once I've got some angular momentum, and I lift my feet off the floor, I will have this angular momentum forever in this direction, and the earth will have this angular momentum forever in that direction. Okay? So that's important. Okay, now let's think about something else here. So, so I should say this. Okay, so there's nothing I can do with my arms, for instance, to change my angular momentum. So suppose I start with 0 angular momentum. I'm not touching the floor. My angular momentum should remain 0 forever, no matter what I do with my arms. Okay, so I can go like this. Like this, 0 angular momentum, 0 angular momentum, 0 angular momentum. Okay, so now you argue that, oh, wait a minute, when your arms are moving like this, they have angular momentum in a downwards direction. Yeah, but at the same time, my body is twisting the other way, and there's angular momentum in the upwards direction. At every instant of time when I'm doing this, my arms have angular momentum in one direction, and my body has angular momentum in the other direction, and so they exactly cancel out. So my angular momentum always remains 0. There's nothing I can do with my arms, moving them, whatever, to change my angular momentum of 0. It will always remain 0. Okay, so it's exactly the same thing as I'm floating out in the middle of empty space. And I've got this block here, and I can grab onto this block, push and pull, push and pull. Okay, so when I push on that block, then yes, the block has linear momentum in that direction, and I have linear momentum in this direction, and they exactly cancel. And then I bring the block to rest, and then I pull it towards me. And so the motion looks like this. Okay, so yeah. At any instant of time, you know, the block might have linear momentum that way, but I have linear momentum that way, and the total linear momentum is equal to 0. Okay, so I can never change the total linear momentum of me and the block. If it starts out at 0, it always remains at 0, no matter how much I flail around and move my arms around. Okay, so it's like, you know, we learn, the idea of center of mass. So, so the net force acting on an isolated system, the external force acting on a system changes or causes acceleration of the center of mass. If there's no net force acting on a system, then the acceleration of the center of mass point is 0. So the velocity of the center of mass point is constant. If it starts at 0, if it starts at rest, it will always stay at rest. So if there's no external forces but only internal forces, then no matter what I do, I cannot change the location of the center of mass of me and all these masses attached to me. Okay, so I can't change that point. Now, angular momentum is a little bit different. Okay, so there's something a little bit subtle about it. Okay, you can't change the angular momentum, but you can change your angular position. So I want you to watch this. This is super cool. Okay, so I'll attach some masses to the ends of my hand, and so right now my feet are off the floor. Okay, so I cannot. So I'm an isolated system, and my angular momentum starts at 0 it always remains 0. Okay? And so what I'm going to do is this. I'm going to move these masses in a clever way. Okay, I'm going to go like this, then I'm going to pull in, then I'm going to rotate the opposite direction, then I'm going to push up, then I'm going to rotate again, then I'm going to pull in, and then I'm going to rotate around, then I'm going to do this. Okay, so at every instant of time, I have 0 angular momentum. 0 angular momentum. 0 angular momentum. Okay, so even though as I'm cleverly moving these masses around, at any instant of time, my angular momentum is always 0. What I'm able to do is incrementally change my angular position. Okay, so that's kind of cool. So, so you can look this up, and there's some debate or whatever. But the idea is that if you take a cat and you hold the cat upside down by its paws, right? And so it's got 0 angular momentum about this axis. If you let go, the angular momentum of the cat as it falls can never change. However, the cat is clever, and the cat can move its arms around and its tail around, pulling in and out and rotating and things like that, in such a way that it can incrementally change its angular position. But at every instant of time, its angular momentum is always 0. Okay, so that's kind of cool. Anyway, so you can look that up. It's really neat. Anyway, so so another thing to say is this. Okay, so I've got these masses here like this, and now what I'm going to do is I have 0 angular momentum right now. I'm going to push off the floor. I'm going to exert a clockwise torque on the Earth. The Earth will exert a counterclockwise torque on me, and angular momentum will be transferred to me. Okay, but then I'm going to lift my foot off the floor and never touch it again. Now my angular momentum can never change no matter what I do with my masses. Okay, so if I pull them in, yeah, my angular momentum has not changed. I push them out, my angular momentum has not changed. But you'll notice something. Something is changing. What's changing is my angular velocity. When the masses are far away from the axis of rotation, the angular velocity is low. When I pull the masses in closer to the axis of rotation, my angular velocity increases. Now, the angular momentum, to be sure, has not changed. But remember that angular momentum, like linear momentum is mass times velocity, angular momentum is moment of inertia times angular velocity. Okay? So now, if you're moving through space with some linear velocity, you can't change your mass. And linear momentum is conserved, so your velocity will never change. However, angular momentum is moment of inertia times angular velocity. Okay, and so you can change your moment of inertia. So it's I times omega. If you make I go down, then omega has to go up, so that the product I times omega, the angular momentum, stays the same. So you can change your angular velocity, okay, just by redistributing your masses. Okay, so remember, when I have my arms out like this, then this mass located far away contributes significantly to my moment of inertia. Okay, because remember that the moment of inertia for a mass located a distance, perpendicular distance r, away from the axis of rotation is mr squared. So when the mass is here, it contributes a certain amount to my moment of inertia. Okay, but when I move it twice as far out, mr squared, 2 squared is 4. This mass now contributes 4 times to the moment of inertia. So out here, when the masses are out here, my moment of inertia, my moment of inertia is large. Okay, but when the masses are in close, my moment of inertia is small. So I'm not changing my total mass. All I'm doing is redistributing the mass further away from the axis of rotation or closer to the axis of rotation. I'm just changing my moment of inertia. So angular momentum is a really cool thing. So since it's I times omega and you can change I, then omega will change to compensate such that the angular momentum is conserved. Now, you might wonder, well, that's a little weird. So if the angular velocity increases, doesn't that mean that your kinetic energy associated with that rotational motion increase? Well, let's think about that for a second. So the kinetic energy for translational motion is 1/2 mv squared, which is the same as p squared over 2m. Linear momentum squared divided by twice the mass. Okay, angular momentum is 1/2 I omega squared. But angular momentum is, Did I say that right? The kinetic energy associated with rotation is 1/2 I omega squared, but the angular momentum is I omega. So the kinetic energy associated with rotational motion is L squared over twice I. Just like P squared over twice M, it's L squared over twice I. So now when I'm doing this, okay, I start with some angular momentum, I take my foot off the floor, my angular momentum never changes. The L squared in the numerator stays the same, and it's divided by twice I. If I make I smaller, oh, well then the kinetic energy is going up. And here the kinetic energy is going down. Here the kinetic energy is going up. Okay, so kinetic energy is going up. How is that possible? Energy is a strictly conserved quantity. Okay, so where's it coming from? Well, let's see. Change in kinetic energy, you can do work. You can transfer energy to the system. How do you do work? Well, force acting through a displacement. Okay, so let's think about that. So when I'm spinning around like this, okay, then these masses are moving in uniform circular motion. And in order to make that happen, there has to be a force on them directed radially inwards. Where's that coming from? My hands. I can feel myself having to pull inwards to keep these masses from just moving on a straight line. These masses would like to continue to move on a straight line. In order to bend that mass into a circular motion, I have to pull inwards like this. I can feel that force with which I have to pull inwards. Okay? And so, if I pull my arms inwards, I pull these masses inwards, what's happening is I am exerting a force in radially inwards. The mass is moving radially inwards. There's a force acting through a displacement. Force times distance is work done as energy transferred. So in this case, it's energy transferred into kinetic energy. Okay? And so where does that energy come from? Energy is a conserved quantity. Well, it comes from the chemical energy inside me. Okay? So yeah. So that's an important thing to sort of understand. And another thing just generally to say is that this idea that when masses move inwards like this, so it's like the skater, right? The skater going around, and the skater pulls in their arms, and their angular velocity increases. This is a super important concept, super important phenomenon that happens all over the place all the time. Like for instance, the formation of our solar system. What we've got is this great big cloud of gas and dust, huge, light years in size, and it's got some random sort of random rotation about some axis, because the interstellar gas and dust there is turbulent, supernova explosions go off and so on. So this parcel of gas and dust, which is going to collapse to become our solar system, started out with some small angular velocity, just random. Okay, but then as it gravitationally collapsed, okay, we're bringing these masses in, and so, but angular momentum is conserved. And so what's required as the moment of inertia decreases is the angular velocity increases. And so that's why we get our planets swirling around the sun like this. Okay, that comes from a super tiny random initial angular velocity, which grows as these masses are brought in and the moment of inertia decreases, the angular velocity increases. Okay, so yeah, so this sort of idea is super important throughout all of physics. Okay, you'll see tons of examples. Okay, so that's a great demo discussing conservation of angular momentum. Okay, angular momentum is really cool.